I'd like to switch on the microphone. Second, I'd like to thank the organizers of this workshop for inviting me, setting up this very nice program. I've enjoying it very much so far. Third, I'd like to congratulate Eduardo. As many people before, I'd like to thank him for the contributions to physics and for educating many good people. I was lucky enough to catch Eric Andrade as a postdoc about 13 years ago, and since then this has been extremely fruitful collaboration, so thank you for that. So, now let's turn to physics. As you see from the title, this is a talk about magnetism and about quantum phase transitions. And what I will do in the following minutes, I will try to entertain you with a story which is a combined story of theory and experiment. And it has been done together with Christian Pleiderer and Andreas Wendel, his student who performed the experiments, and my student Heike Eisenlohr has contributed some of the theory. So, here is what I want to cover in this talk. I will start with a very brief introduction, recalling quantum criticality, and then I will start talking about the material which has been studied here, which is lithium holmium fluoride, which, as you will see, and many of you actually know, is a system which shows a transverse field easing quantum critical point. And then I will confront you with a set of new experimental results, and I will then tell you about the modeling and the emerging picture. So, this is what a phase transition is about. We know and love this. And a quantum phase transition is the same thing now happening at t equals 0, driven by quantum fluctuations in quotation marks, so something which can destroy order in the simplest case upon tuning a non-thermal control parameter. And the standard phase diagram, which has made it to textbooks, looks like this, that there is temperature and some non-thermal control parameter, and you can drive the system in the simplest case from an ordered to a disordered phase. And some of us, at least, are interested in this quantum critical regime, which has some fascinating properties which are beyond that of stable phases. Now, this type of physics, where this here is, let's say, a magnetically ordered state, and that's a quantum disordered state, are observed in various magnetic insulating compounds where the underlying physics is conceptually relatively simple. One nice example is thallium copper chloride, which is a coupled dimer magnet, which starts out here in the quantum disordered phase because it consists of paired spins 1/2, and then upon applying pressure can be driven into an ordered phase. And so this transition is well understood, including thermodynamic and spectroscopic properties. Now, for such a transition, theorists like to write down an order parameter field theory to capture the underlying physics, and for thallium copper chloride, for instance, the order parameter is an antiferromagnetic, so a staggered magnetization, and the type of theory you would like to write down is this phi-4 theory or Landau-Ginzburg-Wilson theory, which essentially captures the dynamics of this order parameter field here called phi near criticality. And we understand the properties of this theory reasonably well, and it's for the following, it's just important to keep in mind that what this thing describes is a coarse-grained version of this microscopic degrees of freedom. And I'm emphasizing microscopic here because you saw in the title there's a mesoscopic quantum phase transition, which will appear later, and it needs to be contrasted to what is captured by this type of theory. Okay, now, lithium holmium fluoride is a textbook example of quantum criticality, and one of the first papers pointing this out included Gabe Apley as an author. So it's a ferromagnet, and you see the phase diagram here as function of temperature and a field that's an easy axis ferromagnet, and that is the field applied transverse to the easy axis. So you see it has a very low transition temperature of 1.5 Kelvin and a critical field of about 5.1 Tesla. And so if you apply the field at low temperatures, then this here would be the quantum critical point, which you might be interested in if you're interested in quantum critical phenomena. Now, the simplest model describing this type of physics would be an easing model, as shown here, where the J now would be negative because it's a ferromagnet and a transverse field. And the competition between these two is what governs this transition. Now, lithium holmium fluoride is a little more complicated. There are some microscopic ingredients which contain physics beyond this model, and I will go through them one by one. The first one is that, in fact, the exchange coupling is relatively small. The moments are large. Therefore, the magnetism is dominated by dipolar interactions. Dipolar interactions are long range, and therefore, both the thermal phase transition and the quantum phase transition are in fact of mean field character. That's something which has been understood a while ago, and that's fine and nice. Actually makes theory somewhat easier. And the second complication is that holmium, which is a magnetic ion here, is not a simple magnetic ion, but it's in fact its lowest state, which is relevant here, is a non-Kramers doublet, which means there's a doublet state which is not protected by time reversal, but by crystalline symmetry. And so it's this doublet which is responsible for the magnetism, and the fact is non-Kramers is responsible for this very strong Ising anisotropy. Now what you see here is a crystal field scheme, so these are all crystal field levels of these J equals 8 electronic moments. As I said, these are large moments, and there is a gap of 11 Kelvin between between the doublet and the next excited state. And as I said, there's the easy axis is along Z in the coordinate system which we'll be using, and there's a large moment along the Z axis in this non-Kramer doublet state, but zero moment along the two other axes, again, because it's non-Kramers. And what you see here is how this lowest doublet splits in a field, and the hallmark of non-Kramers is that this splitting is quadratic, not linear. And it's this splitting, in a sense, which competes then with the exchange interaction. And this is what drives the quantum phase transition. Okay, the last ingredient here, which will be important for some of what comes, is a large hyperfine coupling. So holmium happens to have a large nuclear spin. It also happens to have a sizable hyperfine coupling. And because of that, actually, the effects of hyperfine coupling are visible at scales which are unusually large, in this case, roughly half a Kelvin. And it has been realized early on, in fact, that this rather unusual shape of the phase boundary with this inflection point over here is related to nuclear spins. So in fact, this here is to be understood, this nose, if you want, is to be understood as a hyperfine-induced stabilization of the ordered phase. And I will come back to this aspect later. The fact that there's large hyperfine coupling also means that all excitations we need to think about involve the strong coupling between electronic and nuclear degrees of freedom. So all the modes are properly to be understood as electronuclear modes. And that has been nicely seen in the neutron scattering experiment by Henrik Ronno and collaborators, where they were looking for the soft mode which should accompany the quantum phase transition. And so these results is schematically shown here. Here is field, and that is the energy of the mode they could measure. This second dashed line here is a critical field, and that was the mode they observed. So for a proper quantum critical point, this energy should go to 0, but it doesn't. So there is incomplete softening here. And the reason is that there's another mode, which is down here, which could not be seen in the neutron scattering experiment due to resolution issues. Both modes are coupled electronuclear modes. This one here is primarily of electronic character. The lower one is primarily of nuclear character, and it's a nuclear one which softens at the critical field. Now with this, let me just pause and insert one more general slide on how to think about magnetic quantum phase transitions under the influence of nuclear spins. In fact, if you think about this, there are at least two scenarios what could happen if you subject a standard magnetic quantum critical point to the influence of nuclear spins. One is, that is realized in the lithium-holmium fluoride we are talking about. One is that essentially the hyperfine coupling shifts the quantum phase transition, but otherwise leaves it intact, which then, if the hyperfine coupling is sufficiently small, would lead to a phase diagram like this one here, where at large energy scales you essentially have an electronic quantum critical regime where the hyperfine coupling is unimportant. And then the hyperfine coupling sets in at some small energy scale, it shifts the critical point, and then there is an asymptotic quantum critical regime which is dominated by the nuclear degrees of freedom. And again, if the scales are well separated, there would be two different regimes of quantum criticality, one which is purely electronic and one which is about the combined electronuclear modes. In fact, lithium-holmium fluoride, the hyperfine coupling is so large that you cannot distinguish the two regimes. There is another scenario which one can also envision, and that is, in some sense, more drastic. Namely, you can envision that the quantum phase transition upon switching on hyperfine coupling and disappears entirely. That would, for instance, happen in thallium copper chloride if there were nuclear spins. There are none. Because then you can have an argument that in the quantum paramagnetic phase, the electronic quantum paramagnet, if you couple hyperfine spins, so nuclear spins to it, then they will experience the interaction via the electronic degrees of freedom, so some type of RKKY interaction, which eventually leads to nuclear order all the way. And then you would have a phase diagram like this, where there would be an electronic critical point here with an electronic quantum critical regime, but due to hyperfine coupling, the magnetic phase extends all the way, and there is no asymptotic quantum critical regime, but there is just smearing. Okay, for lithium holmium fluoride, we are in this regime, and that's what we will discuss the following. So now I get to the experimental data, and the new measurements performed in Christian Pfleiderer's group involved not only looking at the behavior of the system in a transverse field, but in a field slightly tilted from the transverse direction. So that's schematically shown here. So we have an easy axis, that's the z-axis over here. We have two hard axes, and we could apply the field really along a hard axis where this angle phi would be 0, and now we have a finite angle phi such that we have some tilting with respect to this hard axis. Now, what do we expect? If we have this tilted field, then we have one field component along the easy axis, so it couples to the order parameter because we have a ferromagnet. So the natural expectation would be, based on Landau theory or on general arguments, that the transition would be smeared. So for perfectly transverse field, the magnetization has this behavior of a transition somewhere, but if you have a finite tilt, then you would expect the transition is smeared, and then the phase diagram would look somewhat like this. But that's now low temperature phase diagram. Here is field, and here is the tilt angle. So at 0 tilt angle, there's a quantum critical point, and you can, by tilting the field in both directions, you can polarize system from up to down. And everywhere else, there would be a crossover. So that would be the only transition at phi equals 0, and what is color-coded here is, in fact, the magnetic susceptibility, which is maximum here at the critical point. Good, that's the expectation. Now let's look at experimental data. So what has been measured in these experiments, again as function of this tilt angle, is the magnetic susceptibility along the easy axis in an AC setup with the main magnetic field, again, applied along a direction which can be tuned by this tilt angle. So this is here the measurement at 0 tilt angle, so this is 0 degrees, and what you can see is that that's at a relatively high temperature, but below the Curie temperature of 1.2 Kelvin. What you can see is at elevated fields, you get this finite susceptibility, that is the quantum paramagnetic phase. And at low fields, you get something which is a constant, and this is in fact corresponds to the ordered ferromagnet, and the fact that the susceptibility looks as it looks is because chi is limited by the demagnetization effects. And this kink here is what symbolizes the transition. So far, so good. And now we tilt the field, and this is what comes out. And what you can see is that there is a feature for any tilt angle, and if anything, the feature of the transition gets sharper. There's no smearing. And the obvious question is why? And this, in fact, extends all the way to 90 degrees. So the experimental observation, if you interpret this here as a sharp feature, which you probably should, is that there is a transition at any finite angle, which, if you interpret this as a jump, it seems to be first order, and the obvious question is why there is no smearing. Here is more data. So this here is at the same elevated temperature. This here is now at very low temperature, and this panel is the real part of the susceptibility, which I showed before. Again, the real part here, and the other two panels are the imaginary part, where you can read of dissipative signatures, and you essentially see that with changing the temperature, not much happens. You still have this kink, which evolves into this jumpy feature. There is one thing here, namely susceptibility goes down at very low fields at low temperatures, and this presumably is related to the freezing of domain walls, because it's actually what produces this roughly constant susceptibility over here is because the system, upon applying an AC field along the easy axis, responds by shifting domain walls. And if the domain walls freeze at very low temperatures and very low fields, then the susceptibility goes down. Okay, one can also interpret this imaginary part. I will not do this here in much detail. So the main thing which you can see is that this critical field is significantly reduced upon tilting the field. That is shown here in this first panel. So you start out at 5.1 Tesla, but already with a tilting angle of a few degrees, you can reduce the critical field by more than a factor of 2. So the system is very sensitive to this field tilt. And what the second panel shows here is a quantification of this supposed jump in the susceptibility, which is 0 at 0 angle because it's a kink, but then the jump increases. So that's the experimental result. And here is again a summary of the experimental data. That's now again the phase diagram thing. You have temperature and magnetic field. And these here are phase boundaries which trace out the feature we have just seen. And at 0 degrees, you have this curve here, and then you see that, again, with increasing tilt angle, this ordered phase, or this thing is much suppressed. And it's yet again shown here. That's the same type of plot where color-coded is the real part of the susceptibility. And that's just to show that you really have this very sharp change in the susceptibility from being small here to being large here. And so here you see the phase boundaries, and the white line is simply the reference for the phi equals 0 thing. Okay, good. So that's what the experiment shows, and then the question is, can we make sense out of that? And apparently, this is beyond what Landau theory predicts. And so it's beyond what you would expect from a microscopic order parameter picture. And then one hypothesis is that this has to do with magnetic domains. And that is, in some sense, also fueled by the fact, you saw this before, that this feature exists essentially up to a tilt angle of 90 degrees, which is where you simply probe the ferromagnet along the field along the easy axis, which is what you use to follow the, you know how this curve is? Hysteresis curve, that was the word I'm missing. Yes, the hysteresis curve. Yes, okay, good. So now, let's try to do some modeling, and let's try to see how far we get. So this now describes our theory contribution here. So we now want to have a good theory which describes lithium holmium fluoride in a tilted field. That's a little non-trivial because of these non-Kramers ions. So this here are the microscopic ingredients which we need. So there are single ion terms. There is a full crystal field term over here. There is a hyperfine coupling to the nuclear spins. There's Zeeman term for both nuclear and electronic spins. And then there is some interaction between the ions. We will treat this in mean field. Therefore, I have not explicitly written down the dipolar form of it. But one complication is actually that one cannot get away with modeling the lowest non-Kramers doublet by a pseudospin, because the field couples to it in a very anisotropic fashion. Again, it's linear in one direction, but quadratic in the other direction, and that's something which you cannot capture by an effective spin 1/2. We tried hard, we failed. Therefore, one needs to take into account all crystal field levels. And there's a nuclear spin, which at the end means locally we have a Hilbert space of 17 times 8 dimensions. That's what you have to cope with. And now we do mean field theory with this local Hilbert space. That can be done. It's not that complicated, because at the end it's a doublet which orders ferromagnetically. I'm just telling you, if I want to do this quantitatively, and here, as you will see towards the end, we managed to get this quantitatively. I have to work a little harder than just thinking about a spin 1/2 model. If I were satisfied with qualitative aspects, I would just do an Ising model. But I want to get numbers right. Okay, now domains. So this is something which actually people have done before. So this is what is in the literature, and you see references down here. Now what we did is we included domains, and so there are of course studies of how domains in lithium holmium fluoride look like, and that's complicated. But we make some simplifying assumptions here, which turn out to be not so bad. So we assume that domains are sheet-like, and we just assume we have 2 types of domains which are up and down along the easy axis. And the main thing then we treat the domain sizes as variational parameters in a sense. And the main thing which we will have are the widths of the two types of domains. So we have green and blue, up and down, and the widths will be variational parameters, as are the magnetizations in the domain. Okay. And so we can, with the setting, we can actually compute we can compute the stray field energy exactly. We can take the domain wall energy from Monte Carlo simulations that's known. And then the only fit parameter which we actually have is, well, we have the domain size, this variational parameter. The only fit parameter will be this coupling constant here. So we now, by doing this, we have a consistent mean field theory for this Ising ferromagnet, which has domains. And so at the end, we have to solve coupled mean field equations, and they look like this. And, well, you crank the handle and do it. And here is what comes out. So first, we look at the transverse field case. And now these little pictures, I hope that you can see them. They qualitatively indicate what happens. So again, perfectly transverse field. You start out with a sample which has equally sized up and down domains. And actually, these arrows, the red arrows here, show the magnetization along the easy axis, and there are little arrows here on top which show the magnetization in the transverse direction. And then you increase the field. The domains stay essentially as they are. The magnetization, the spontaneous magnetization diminishes, and there's an induced magnetization in the direction of the field. And then there's a critical field, and this is where two things happen. Namely, the spontaneous magnetization disappears, but that automatically also means that the sample becomes single domain, right? Because there's no reason for domain formation anymore. So, and that is the transition in perfectly transverse field. And you see this here. You have the magnetization in the up and down domains that go to 0. And there is a domain ratio, which is this quantity V here, which starts out from 1/2, meaning we have equally sized up and down domains, and then simply goes to 0 because there's just single domain. OK, that's in some sense trivial. And now we go to the tilted field case. And here is now the interesting thing. Its sample starts out in the same configuration. Now you apply a tilted field, which prefers up domains. And what happens is that the up domains get larger than the down domains. And that goes up to a transition, which is now a transition where nothing else happens but the domains disappear. And the domains disappear by squeezing out the minority domains. So this you see here in this brown curve, which is a domain ratio labeled on this axis. It starts out at 1/2 of equally sized up and down domains. This domain size ratio goes to 0 at this transition field, whereas the magnetizations are non-critical. So the magnetizations are finite, and again, the transition is about the disappearance of the minority domains. Okay, so that's what we have. And we have now two types of transitions, again, one for the perfectly transverse case and one for the tilted case. And we can look whether this, what we get, agrees with theory. So here is a magnetization curve, and here is a susceptibility which has been measured experimentally, and this is showing experiment and theory together. And interestingly, our calculation gets all the demagnetization effects automatically right, because we include all the stray field effects in full glory. So we get this constant, this plateau over here, and we also get that this transition evolves from a kink in the perfectly transverse case to this jumpy feature in the tilted case. And here is now the phase diagram comparison between experiment and theory, so dashed and solid. And apart from the fact that we have some slight mismatch in the 0 field critical temperature, which we have not been able to trace down, there is very good agreement in all the other features here. And again, there's only one fit parameter, which is the coupling constant. There is no hysteresis. So, well, the statement is the experimentalists looked hard for hysteresis, and there was nothing noticeable. So, I mean, depending on how you run the experiment, there is a mini hysteresis, but this is nothing which is significant. And the theory, of course, is agnostic to various things. So you can say many bad things about the theory, but there's no reason to have hysteresis in this type of theory. The main question which you are driving, it is a transition first order or second order. And I will come to this in a second. So before that, I will just advertise one more thing, namely, as you saw from this comparison here, this hyperfine nose, this effect, with this hyperfine induced stabilization of the ordered phase, this disappears if you tilt, right? That's the key thing. This inflection point is gone with already a tilt angle of like 5 degrees. And this actually you can understand. First, you have to get clear why does actually hyperfine actually stabilize the ordered phase in the first place. That is actually not just because there's a large hyperfine interaction, but because there's large hyperfine interaction plus a non-Kramers doublet. Why? Because the non-Kramers doublet has the property that it has a large magnitude along the z-axis, but a small magnitude perpendicular to the z-axis. Therefore, the electronic moment is only large within the ordered phase, but small outside the ordered phase. And the hyperfine interaction now wants large moments, right? It's just a magnetic interaction. It wants large moments, and therefore the hyperfine interaction prefers the ordered phase. But once you tilt, and that's written down here, once you tilt, the variation of the electronic moment is actually no longer large because you always have a component parallel to the EZ axis where it's large. Therefore, the variation of the electronic moment is much weaker, and therefore this hyperfine interaction does no longer stabilize the ordered phase. And that nicely comes out of the calculations that also we have done a competing, so an alternative calculation with actually the Kramer's moment, and then this effect is completely gone. So that's all consistent. Okay. Now, last remark here, how to think about the transition. As I advertised, we now have two types of transition, and they turn out both to be continuous. The one which we all know and love is the ferromagnet to paramagnet transition for the perfectly transverse case, which again is at the same time a multi-domain to single-domain transition, which many of us would consider trivial, I mean, if asked beforehand. And this, in this case, has mean field exponents because of the dipolar interactions. But then there is this multi-domain to single-domain transition for tilted fields, which is a mesoscopic transition because it happens on mesoscopic scales. And this is characterized by the vanishing of the minority domain volume, and this appears continuously, right? This thing vanishes continuously. That's the result of our calculation. That's consistent with the experiment. And if you want to do the math, you see that this transition can be characterized by this set of utterly trivial exponents, but it's a continuous transition. And the fact that gamma is 0 here implies that susceptibility jumps. So in this sense, this is a very special type of continuous corner phase transition. And again, it's mesoscale. Good. I have a few data on heat capacity, which I will jump over in the interest of time. There is heat capacity data, which is also interesting and one can think of. And here are my conclusions. Thank you.
Thank you very much. We have time for questions. I think you are first. Oh, yeah.
Yeah, very nice. Could I ask if you looked at the shape, the sample shape dependence of this? Because obviously the domains will be very different for a plate than this is presumably done on a. Could you maybe tell us the shape of the sample that was used here?
Yes, I have. Well, I'm not fast enough to get there. The sample was not a cube, as these pictures suggest, right, but the sample was a sphere. So the sphere has been deliberately chosen to minimize effects of inhomogeneous field distributions. Mm-hmm. And so this entire set of experiments has only been done with a spherical sample. Mm-hmm. Now, for other sample shapes, one could suspect that this transition, which I'm advertising here, would be more smeared because of inhomogeneous field distributions. The theory, of course, makes a lot of simplifying assumptions. We have simply asserted that there's this sheet-like shape. We have played a little bit with it, and in our theory, we come to the conclusion that the energetics of different shaped domains, it doesn't make too much of a difference. I mean, domains are certainly much more complicated, and the referee was asking whether we have any direct evidence for the story, because there's no domain imaging here. So apparently, and the answer is no. I showed you all the data.
But and if we get to chi double prime, is there any indication of some kind of quantum roughening of the walls or anything you could see in the chi double prime? Because of course this means that the walls are completely flat in this picture. So if there's roughening,
in this picture the walls are
flat in your calculation.
Of course.
The question is then if you look at chi double prime, whether there was any indication that the dynamics.
That's too slow. Yeah, so that's of course a well-posed question. I mean, it's clear that the theory we did is a baby theory. Yeah. There are two things here. One is that first, if you look at the real part, you see that this thing is not sharp, right? There is a broadening, and that is presumably due to inhomogeneous field distributions in the sample. So in other words, this is not just a transition which happens at once over the entire sample. And there are dissipative features here which one can track down, but we have not been able to to really interpret them. Let's put it this way. An experiment is underway to image this, and then we will know how the domains look like. And there are, of course, a number of assumptions here in the theory which have not been backed up by experiment. For instance, the critical parameter which I advertise is the ratio between the two domain types. Whether the global size of the domains also significantly changes when you approach the transition is something which we do not know at this point. Theory would indicate that this is a minor effect. But one very interesting question we are thinking about right now is how to think about this quantum phase transition, for instance, when you approach from the high field side. There is an instability. How to think about this instability, how to think about this critical mode. It's a mesoscopic thing, it's non-trivial, and well, that's work in progress.
Hi, so could you explain again what is the meaning of the transition in the case where you have the minority domains collapsing? I mean, there are no broken symmetries, right? So I'm just trying to understand what is is it because the spectrum of excitations are different, but even though the symmetries are the same, or in other words, what allows you to define a quantum critical point, I guess?
What happens here is you break translation symmetry.
Okay. Okay. So it's like a stripe to a uniform phase transition. Okay.
Yes.
Okay.
So you're perfectly right. There is no magnetic symmetry broken because the field already breaks it. But it's very clear it's translation symmetry which is broken, which allows this to be a sharp transition. Now, in the real sample, of course, the domain arrangement is not perfectly periodic. Now you may question how important this is for the entire story. And as I just said, I mean, experimentally, the transition is not perfectly sharp, which may be related to this. But at least it's clear, and I guess in hindsight, it's entirely obvious. You must go from multi-domain to single domain, right? And so this transition must be there.
Well, if you, do you have any interference? Because you have two size scales in the problem. Now, one would be the correlation length, if you would have not a mean field, but with fluctuations, and the other would be the size of the domains. No? I think the interference between these two sizes would be important to.
You're perfectly right. That's an extremely important aspect. We have not started to dig deeply. I mean, you can first ask this question here, right? Because for the standard transverse field case, I mean, this is something where, according to microscopic theory, the magnetic correlation lengths would diverge. And apparently, if this picture is correct, this divergence would be limited by domain size. And this apparently would cut off critical fluctuations, so which means if we were below an upper critical dimension, you would have some cutoff of critical behavior. There must be a crossover to something else. Now, since this is mean field, this is somehow a moot question, but still it's interesting to ask. Now, in this case here, a situation is different because there is no magnetic correlation length diverging, right? Because magnetic properties, magnetic microscopic properties are not critical. So the only thing which may be critical are the things associated to translation symmetry breaking. And again, how this precisely works is something we are trying to figure out right now.
Sorry, it's me again. I forgot to ask my second part of the question, which is, this is an insulator. Suppose that there's no reason that this couldn't happen in a metal, right? And where these degrees of freedom are going to couple to the electrons. What would mean for this quantum critical point now if you allow for coupling to electrons? Is there something non-trivial about it? I assume so, right?
Presumably. So first of all, you are right. I mean, this scenario is extremely generic for any easy axis ferromagnet. Even easy plane ferromagnet can do this, right? I mean, you go from multi-domain to single domain, that's clear. You can actually also think about this in a ferroelectric, by the way. You can play the same game. When this couples to, so I mean, one thing to keep in mind is that this is a transition happening on mesoscopic scales, which means, and that's also what we see in the specific heat, is that does not leave much imprint on thermodynamics. So it's very significant in the susceptibility, again, because susceptibility comes from the motion of domain walls, so that's precisely the degree of freedom which is involved here. But specific heat, so we have a nice set of data, but if you tilt significantly away from the easy axis, then there's essentially no thermodynamic transition, no thermodynamic signature of this transition. Now, having said this, I'm not sure. So again, this is a mesoscopic scale thing. So you could imagine that there is a long wavelength, non-trivial long wavelength influence on the electrons. We have not thought about this.
Well, so at zero temperature, there's a transition zero temperature. This transition, is this actually a real quantum critical point with a quantum critical region? I missed that part. Is there a quantum critical region where in a narrow range around the critical point you can use a much simpler theory or not? I'm sorry if I missed you explain.
I didn't say anything about this. You didn't miss anything. So the modeling here is mean field. So in other words, there is not too much of real quantum criticality. In principle, the answer is yes. There must be a quantum critical regime, presumably at rather low scales, as I just said, because it's a mesoscopic phenomenon.
But here there is no quantum in this model, right?
Well, I mean, these calculations are zero temperature. So, right. I mean, again, this transition is about breaking of translation symmetry at zero temperature. So this is a quantum critical thing. Yes. And the experiment has been done down to 60 millikelvin now. Whether you're satisfied with this or not is a matter of taste.
But in the classical, like in Sajdev's book, there is even in mean field infinite range model, there is a quantum critical region which you can define and calculate with rotors and everything, right?
Yes, yes. So this should be very similar here. Again, what we are just in the process of doing is we are trying to work out a critical theory for the mode softening when you come from here to here.
So there should be a much simpler theory for that around near the critical point, right?
In principle, yes. So the clear answer is yes.
And final question. Press a button.
Take the perspective that you're describing a stripe ordering transition. I would naively expect a cubic term in the effective Ginzburg-Landau free energy for the stripe-like order parameter. Is that false or?
Ask me in 2 months from now.
Okay.
So I perfectly understand what you're saying. You have to keep in mind that this is not a garden variety stripe transition, because again, it's not simply about breaking translation symmetry by the lowest harmonic, by establishing the lowest harmonic, but it's about inserting minority domains which have zero width to start with. So it's a highly unharmonic thing, and therefore I could imagine that the rules of the game are changed.
Okay, I think